Okay, the class is started. If you have read the notice I've loaded in the website in Aula Web, you see in general the comments about the study program and some important news for the I call them late enrolled students. We have many students that for external reason couldn't attend since the beginning the course, but they want to attend and to do the exam. And for all of them, but not necessarily students who enrolled late, simply for all the students who decide to do the exam, to pass the exam at the end of the second semester. I'm talking about the Italian degree, not the double degree, because they are forced to pass the exam at the end of the first semester. But in general, all robotics engineering students can pass the exam at the end of the second semester or later. Well, to stay in course, they must do at the end of the second semester. In that case, you know the rule because I told you several times, and they're also written. So assignments are compulsory, and there will be new assignments in the second semester, delivered during the second semester with proper deadlines. And regarding the program, the study program, well, there are no official classes in the second semester, so the course is over now in this semester. But well, you have the recorded classes. You have all the material in our web. But I am available, and I will do. This is the idea, to have one class per week in any case. So in which to have comments on explanations, question and answers, and so on, just exactly synchronize it with the first semester course. So in any case, for students who decide to study and to pass the exam in the second semester, we will have one class per week. I don't know which is the schedule, which will be the schedule, will be decided after all courses are properly scheduled. So we will do that. And in any case, I'm also available for just for helping all of you who need some prerequisites that are not satisfied. For example, basic C programming or something like that, or the organization of an operating system and so on. Well, the course in the official program, there was the last topic in the course was the D-bus. I decided to drop it. The bus was just an example of higher level distributed or concurrent programming in the Linux or Unix Linux environment. A higher level with respect to POSIX, in which all processes can share resources at a higher level. It's a quite simple system that is similarities with other popular systems in computer engineering, like the .NET framework in Microsoft, or .com, or other frameworks. I decided to drop because the examples in the bus are simple and good we use a graphic interface. But since the virtual machine has no graphical interface, I decided this is not the case to do that. Well, some concept in higher level frameworks for communication will be given in the software architecture for robotics. So it's not a minus for you, nothing to do. Well, I have just one topic that I want to comment today. There is a purely theoretical topic that is addressed also in the real-time operating, the real-time systems course that many of you probably are following, and many of you already know if they come from, if you come from computer engineering or related degrees. Some of you may ignore completely the topic and has been addressed in the previous lesson. So I have just to do some theoretical information, and next week, and I will give you also some material, even if the material was not foreseen in the origin. So I decided last week to grab and to steal some good material. I think I took it from MIT. I don't remember. Well, it's a very good course. So I just cut some slides, very synthetic and very clear, and apologize for that. But I think it's better to show the slide in the original structure instead of copying and pasting in new slides. I'm not the author of them. You can see a lot of materials about this topic. What's the name of the topic? Semaphores. Just to have some important information and about semaphores and what they are for. Yeah, we have seen semaphores in the shared memory, and if you have to study the slide of shared memory, not to code using shared memory, but you have to know the theoretical information. Those of you who are following the real-time course have used semaphores and critical regions in reduced environment, reduced horizon of problems. And I want just to show you just 10 slides. I will upload the slides today. And I'm asking you to be aware of those concepts, even if you don't are asked to write code regarding this. But maybe they are useful also for students following the real-time course. So semaphore, which is a semaphore? Now I share the screen and I show you some concept. Maybe at the end of the course, I've learned how to share properly the screen. So I apologize if I do something that doesn't work, but in any case, let me share the screen. And you tell me if you really see. Now I share my desktop. Okay. And then can you see my scratch pad, the paper? Or can you see?
No, Professor.
You don't. Okay, it doesn't work. So I didn't learn to use the the stop share, start again. Oh, terrible. I have to attend some course in using Zoom. Even if I'm using Zoom since 2 or 3 years. Well, now I share this, but I don't have the. Now you see my drawing.
Yes, we can see it.
Yes,
Well.
Professor.
Okay, you see my drawing. Here is it. So first, some concepts, terminology, critical what is a critical region of code? A critical region is a piece of code that in a concurrent environment, in a concurrent program in which several codes are executing simultaneously, is a piece of code that must be executed singularly, just by one process. One process, that's the idea. The typical case is the situation in which several processes, P1, lines of code, P2, lines of code, P3, and so on. There are lines of code that access a shared memory. If these lines of code access the shared memory, and these lines of code access the same shared memory, we say that those regions the critical region and the critical region, those regions of code, those lines of code are critical, so they must be mutually exclusive. So another term is mutual exclusion. Mutual exclusion means it's a technical or scientific term that says that two or more processes are mutually exclusive when executing some lines of code. What is the simplest or the most evident situation? The typical situation is that of shared data, not necessarily memory, main memory, can be file or memory. We have encountered this situation well, and we didn't solve problems with this these characteristics, but we have seen there are system calls using files exactly to solve this problem. If you remember, when you open a file, you have also system calls that are called locking, unlocking. Locking, unlocking in POSIX terminology is a way of solving the mutual exclusion in the case of a shared file, so a file accessed by more than one process. So locking, unlocking are syscalls is the primitive in POSIX. In POSIX with IPC implemented as file descriptors or reading and writing. In that part of POSIX, locking, unlocking are the primitives for solving the mutual exclusion or the critical region of code. And this is the typical case. Why you need that? Because simply, I don't have to do, well, I can scratch here. If you have a process, if you have a file with the records, the one process writes this record and another process writes simultaneously this records. Simultaneously means in concurrency. We don't know exactly which are the timing. It depends on the scheduler, of course. But well, this series of records, at the end, if you allow them to write concurrently with no mutual exclusion, at the end you will have what is called data jamming, because some process, the last process who writes this record will be the process who won the access to the record. What was written previously is erased, and so possibly you will have records containing a fusion of all data written by P1 and P2, and if you read the records, you will see just jam. So we have to exclude. In general, the principle is that writers of shared data must be mutually exclusive. So they must have critical regions. In general, any writer must exclude any other writer or any other reader, because this happens also if you are reading and writing simultaneously. Not necessarily it happens if you're accessing only in reading, of course. Reading does not need mutual exclusion. So the first term I want you to know exactly is the concept of critical region and mutual exclusion. Related concept are two terms to refer to the same concept. Regions of code that must be executed separately, just one at a time. How you can do that? In the specific case of files, you can use the system call that is called lock unlock. When you decide to write on a file, you lock. The other processes who try to lock are delayed until the first one who locked the file unlocks it. That's the simplest way of performing mutual exclusion. This is the first concept in general. Those of you who have learned to program using threads know that this is it. Threads are sharing all memory, I mean all data structures that have been declared before threads were activated. So this is typical of thread. Typical. Anytime you have a shared memory between codes executing concurrently, you have the problem of mutually excluding codes that access the same memory. This is typical in threads, but if you remember, it is also possible using the POSIX shared memory that is more tricky than using threads, but can allow you to have the same shared memory structure, so memory data, common memory data between processes and not between threads. So this is how to protect access to shared memory You can use lock, unlock. Lock, unlock are only for files. You need some new primitive, and the new primitive is the semaphore in black. The semaphore is, well, has several purposes, but in principle is to implement mutual exclusion. And therefore, as a consequence, also critical regions is equivalent in a sense to lock, unlock, but well, for those of you who know, or you will learn after, lock is a semaphore in principle. Sorry. Wait, the nymph. Okay, it's 9 o'clock. Semaphore, locking and unlocking are, from theoretical point of view, exactly binary semaphores. We have seen just on paper, on the slides, in the slides of regarding the POSIX shared memory, which are the primitive the system calls for to implement semaphores. But surely you didn't catch the meaning, even if there are examples inside. But it's better just to have the information regarding semaphores, to have purely theoretical examples, and that's the examples I want to give now. Purely theoretical, I mean not reading codes for solving a specific problem, but just having the general idea. So a semaphore is a primitive. A semaphore is in POSIX threads. In POSIX thread, there is a semaphore, there is for threads, but also POSIX shared memory. The two semaphores are different. Logically, they are the same concept and implement the same mechanism, but are different entities in POSIX that are obtained by the system in two different ways using different calls. If you are using POSIX threads and you compile your code with the pthreads switch to the pthreads option, you have the semaphore, the thread semaphore, and also some reduced semaphore that are called conditional variables. If you are using the shared memory, use a semaphore that acts in a different way, but logically is the same. And now I want to browse the concept of semaphore using the MIT slides. Okay. Questions? No questions. There's some additional terms. Well, probably, well, I think that in a different color, just to have just only one slide. The concept of, you know what is a deadlock? We have seen a problem, and we will see again the problem of the dining philosophers, in which I've asked you to solve the problem and give some code, and we have code written by one of you and will be published. Deadlock is a situation in which several processes in a concurrent system are mutually waiting for something that should happen circularly. So it's a symmetric situation in which there's no computation, possible computation. The situation in the Dying Philosophers, that is a typical problem to explain a general situation of deadlocking and which are the ways of solving it, says simply that there are several processes. In that case, there were 5 processes. Two, three, four, 5. There are 5 processes, and each one was waiting for something happening that had to come from by the other process. Deadlock is always symmetrical and is something that must be, in any case, avoided. In POSIX, it's difficult but possible to design an architecture with deadlocks. In the case of the Dying Philosophers, it was just a case in which it was clearly possible. And in any concurrent system, deadlocking is possible. So you have to design the system from the beginning. We also have seen some practical examples in which the idea was to have a monitor that was just looking if processes are computing or not, which is a practical situation in which you not only write your code for your problem, the solver problem, automation, robotic problem solved, but also you implement, since you're not sure that no deadlock will occur, you also implement a monitor that checks if all programs are computing or not. This is a practical, technical solution for that. Another term is, well, you know, thread. We are thread. We are widely use this. The concept is of, they're called also lightweight processes. So light processes. Logically, they are processes like our POSIX processes, but they're lightweight in the sense that they, in the internal architecture of the Linux Unix, they are part of only one process, but they are scheduled as just like they were separate processes, but they share all resources, all open file system, but also all the memory and so on. And they are called lightweight because for the point of view of the kernel, they are easier to manage and they need less resources inside the kernel, so they're faster. And but the problem is that they share all the, well, it's not a problem, is the feature. They share all the memory. So all arrays, structures, variables, and so on defined in the code are shared by all lightweight processes, single processes acting concurrently. So they always need systems for mutual exclusion. In our case, in the POSIX, in normal POSIX, we are not, shared memory is an exception in a sense, and you are not coding using shared memory. And in that case, mutual exclusion is not so important, but it's all in any case important. So this is the definition of thread. Go into the internet, you will find the term. Another term that probably I've used and I will use and is in the MIT slides is the concept of race. Race is a definition, is a theoretical definition, but means that the effect of a piece of code is different depending on the speed of the execution, or what is the execution, the effects of the side effect of the execution of other processes or threads. So a non-deterministic result output, different from non-determinism that we have defined in reading data using the select in our case. Race is just a feature of several codes acting simultaneously. And if you do not foresee that they can interact, the output is cannot be foreseen. It is not deterministic, but it's not deterministic in the sense that it is useless. The typical case of race is the access to shared data without mutual exclusion. So if P1 writes here and P3 writes here with no mutual exclusion, the result at the end of writing is what I call jamming. It's a random result because data are the writes and erase the previously written data and so on. So this is a case of race. The races can happen in several ways, but the context in which we are discussing is that of the race is the typical result of a lack of mutual exclusion of protection in critical regions. That's all. That's all, folks. Regarding terminology, I wanted to be clear in that. We don't know what. Okay. Let me save it for future enhancement. Okay. Now we can open the MIT slides and have a look for the theoretical definition of semaphores. I will upload the slides in just today. Okay, questions? No questions. Now I share the screen with the slides. Well, no, let me open the slide using the X or no. Okay, can you see this slide with semaphores, with the heading semaphores?
Yes, we can see the slides.
Okay, semaphores. Well, from a purely general theoretical abstract point of view, a semaphore is an object. As an object is a very simple object, it's just a number. As a private counter, a waiting list, you will see what is a waiting list, because the semaphore acts with the scheduler or with the switcher in the Unix Linux terminology. So it can change the state, the computational state of a process, and put in a waiting state. So it's a waiting list on this object. And two methods or functions. The two methods, so this is a C++ or object programming terminology, but in any case, two functions. And in general, the origin of the semaphore that was designed in the years 60 by Dijkstra the Dutch scientist, as two primitives, signal and wait. So the semaphore has inside a counter, you would say, what is it for? And a waiting list for processes. Wait. The semaphore must be initialized. So and the counter is this value. When you call the wait on a semaphore, you decrease the counter, and if the counter goes below 0, the caller, so the process that has issued the wait, stops. So it goes into the wait state. By the scheduler. So you see now that the primitive is a system call. There's a semaphore, in any case, it's a system call because it interacts with the kernel. It's not a library function. And blocks. This block is the wait state. If the, well, it's not necessarily who sends the wait is blocked, it goes to the wait state. Only if the count goes below 0. If the actual value of the semaphore is 5, at the end of the wait, the count will be 4, but no block. The signal is the dual primitive. It increments the value of the counter, and in case the value of the counter is less than 0, it removes the process from the waiting list. So from waiting state to ready state. So resume means that the process P, which is able to run again, not immediately running, is just ready. So it depends on the scheduling policies that you know, because we have learned them in the beginning of the course. Which is P. P is retrieved from the waiting list. So the waiting list was a list of processes or threads in general that had been blocked by a previously issued wait. So the idea is that if there was some process blocked waiting for the semaphore, make it run again, free to run. So that idea, add to list and remove P, are dual primitives. Add to list, P was added to list, was the process that decided to wait. And signaling the semaphore is just a way of telling the kernel, I don't know who, but pick up the first in the queue for the process waiting and resume, in the sense that make it free. It is important to say that in any case, written in this way, the count variable, count data, the counter, is the number of waiting processes. This is the reason why the check is minus 0. The waiting list usually is the first in, first out, but theoretically is not important. So the correctness of a program or the concurrent program should not depend on the particular implementation. So in any case, the idea is no race. So even if there are priorities, or instead of first in, first out, you can use last in, first out, doesn't matter. Conceptually, your concurrent program should not depend on this. Well, it's just a theoretical reminder. The caller waits may be blocked, not necessarily blocked. May be blocked in the call to wait, but the caller is never blocked, and not typically another caller. When we say the caller, we mean some process. A process is never blocked when signals is to say, okay, if someone is waiting, is free. If no process is waiting, no operation. But in case of wait, you may be blocked or not, depending on the value of the counter. This is the very important note, most important note. Waiting signal must be executed atomically. Atomically, what does it mean? It means that, in particular, these actions and these actions are in their turn critical regions in the definition I've done before. Critical regions means that only one process, I say process, but thread is the same thing, can access this code. The reason is that you're affecting this variable. This variable is shared. All semaphores share a variable between all processes that using the same semaphore. All those processes share this variable. So since the variable is shared, it must be in a critical region. All operation on this variable, and the only two operations are wait and signal, must be mutually exclusive. So to implement a semaphore, you need a semaphore if you want to make the exclusion. That's the reason why semaphores can be are available and managed only by the kernel. The kernel is the only entity able to define a semaphore, because this is a critical region. If two processes simultaneously issue a wait, of one process issues a wait and another process of the signal, one of the two must have access to the primitive, and the other has to wait until the first one has terminated this code. Atomically, another term, atomically, and not uninterruptible. Otherwise, race conditions, that means that you cannot foresee what happens. So these excerpts of code are just the excerpts of code inside the kernel. You cannot write the code for a semaphore. Surprisingly, there is a possibility of writing code without being the kernel. Is not an efficient code. It's called the Decker's algorithm. Maybe someone is interested in that, and ask, and I will explain. And it is possible to do that, but is inefficient, uses busy waiting, but is implemented inside the multi-core processor today, just to have fast semaphores and inside. In any case, these are inside the kernel, which is the way of doing, how the kernel makes those codes in a mutually exclusive way without, implement the critical region in a very, very simple way. The kernel disables interrupts. The kernel, well, the kernel disables interrupts. If you remember the operating system architecture, you know that the only mechanism that asks the switcher or the scheduler to interrupt the process sometimes is an interrupt, an external interrupt or internal. Internal interrupt is comes from a signal or from a system call. But in that case, there are no internal interrupt because your process is executing the wait or the signal. So the only thing you want to avoid is an external interrupt coming from the clock, for example. The clock asks the scheduler to switch some process and to put the actual process in a waiting list, in the waiting state, and to resume another process and so on. If you don't have external interrupt, your code is executing sequentially with no possible interruption. So the atomical execution of a semaphore code is obtained basically and simply by disabling interrupts. Well, disabling interrupts is not a good thing. You must do very rarely, and for example, you lose the system clocks, for example, and that's a terrible damage for the real-time execution and so on. So that's one of the reasons semaphore are very valuable primitives, and you must use the minimum number of semaphores. The typical use of semaphore is mutual exclusion. Countdown lock is a mutual exclusion, but including also a counter. It's not necessary, but you can use it. If you have time, we will see just one example with a counter, and use also to notify an event. Well, it's not a signal, so it's not an internal interrupt. Is a condition that some other process can check, and knowing that, for example, it can do some actions. This is the basic situation in which we use mutual exclusion. The term lock recalls exactly the file locking, the file description, the file locking in POSIX, because it's absolutely the same idea. So please use this general concept to read the slides regarding the shared memory, and in the slides in which semaphores are described in terms of system calls and the example during semaphore. The idea is that if you have two processes, we don't know for what, but you desire, you want that you have a critical sections. So inside the process one, there is a piece of code, some lines of code that must be mutually exclusive with respect to some other lines of code in process two, you simply use this scheme. Use one semaphore, just one semaphore shared by the two processes. And this is sort of a traffic light that tells the two processes if this region of code is available or not, or if part of a file is free or not. So it's an implementation of locking, unlocking a file, and the same. So using the car traffic and the roads as a metaphor, we can say that the semaphore, and that's the reason why it is called semaphore. Semaphore states that some road can be is open or not, so that the car can access the crossing or not. One signals that you can, or you are driving inside the crossing, so all other cars are stopped and vice versa. So this is typical situation. S is 1, and S is the counter. In this case, it says that only 1 can go inside the. In case you initialize the semaphore with a higher number, in that case, is a limited lock. It's not so common certain problem, but in that case, the region may have process 2, process 3, process 4, process 5, and so on. If all processes sharing this semaphore can access the region, but after 3 wait call by all processes, not the same process, but other processes, the 4th process is blocked because it must wait a signal. This is just a case in which you notify something. Well, let's skip. These are dynamic philosophers, but suppose that the critical section is just accessing a shared variable. For example, if you have here semaphore S, well, int if int x equal 0, doesn't matter. Here inside you want to write x, assign x some number, 10. Here you want to assign x 11. So it's a typical situation in which you don't want to allow all the two processes to make this assignment, to the variable simultaneously. This is a very dumb case, but in general, you want that it's a more complex, and you want to do in mutual exclusion. In this case, you protect the region by wait and signal. The first of the two processes, the first one who is able to call the wait, prevents the other process to go inside the region, and vice versa. And this is also the case if you have several processes who write the variable and several who read the variable. In any case, this is waiting and signals. This is just a pattern for preventing the access to the region. Let's go to this case and see how semaphore can define the solution that you already have discussed the problem. and sold in a different with the different paradigms. In particular, in that case, you did not have shared memory, so you had to define a process for the chopsticks or forks in our terminology, and to exchange messages using pipes to decide what to do. The dining philosopher is an important theoretical problem, metaphorical problem, that has the characteristic of being funny, so it is simple to learn, but it in scientific literature and in general in also in any book for learning concurrent programming is used because it includes captures the nature of many concurrent problems, and in particular the concept of concurrency and deadlocking, and can be implemented in several ways. In particular, you have discussed it, and some of you had solved the problem using processes and inter-process communication based on messages and on file descriptors, typical of POSIX, but can be solved also using the shared memory paradigm. And in that case, we called the forks, here they're called chopsticks, is not, well, it's the same thing. You see here that the main code of the philosopher is similar to the one that you have discussed. The chopsticks are shared by all the philosophers, so by all processes or threads, and chopsticks are in an array, and we also have 5 semaphores, an array of semaphores. Since we don't need the counter, we just want to prevent the access to a chopstick, mutually excluding the use of the chopstick. Just only one process can access the chopstick. We initialize the semaphore, all the 5 semaphores to 1. The critical regions is just having the chopstick. There are no codes related to shared memory, but so in our case, for simulating the problems, you spend some times. So you simply block the chopsticks. The philosopher I blocks the chopstick I, and I plus 1 modulus 5, as you did. Taking the chopsticks is just wait. So blocks the chopstick using the wait primitive and releases the chopstick using the signal primitive. So that's the solution, simpler than using the pipes and file descriptors and so on, since in practice there are no need of communicating between processes. Just the communication is centralized using the shared semaphore structure. The problem in that case, is that, so this is common, these are comments for the code. Each philosopher is an endless loop, thinking, wait, well, wait for my, wait is just waiting that the chops is free, but waits in the sense that wait and keeps blocked the chopstick as soon as the philosopher is able to execute the wait. So the wait potentially blocks the philosopher, but makes it run again as soon as the chop is available. And from now on, the chop is blocked again. You release with using signal. You know that this solution doesn't work because it is possible to see a situation in which the five philosophers simultaneously execute the wait, and they can because there are 5 forks, 5 chopsticks available. So there are simultaneously, it is possible there are 5 wait executed, and after that nobody will pass the waiting because all 5 philosophers are executing this. And the program deadlocks. There are many possible solutions to that using semaphores. But all solutions share just one concept, just to avoid the total symmetry of the solution. Here in these slides, one possibility is simply to decide that one of the philosophers is different from other philosophers. It is called the weirdo. The weirdo is the strange philosopher and is being chosen the fourth one that is different from the other, because it has it has priority in taking his chopstick. This is one of the solutions. In general, it is possible also to decide that one of the philosophers is able to do that. This is one possible, the simple solution. Another possible solution is provide an additional semaphore outside the table that says let only 4 philosophers to sit on the table, and only when all the 4 philosophers started eating, we can admit the 5th one, and so on. So there are possibilities, but in general, look at this solution, you will find several ways. But the philosophy of the philosopher for solving the dining philosopher's problem is just to avoid symmetry. And this is in general the way of avoiding deadlocks in general. I want just to point out also this problem that is, well, dining philosophers is theoretical problems that in real life doesn't happen in general, but the theoretical elements of the dining philosopher problems many times are a critical concept. So that's the reason why we always teach the dining philosophers. This is on the contrary, this is a problem that has in many practical cases, typically on low-level programming, so efficient programming, is is common, as to say how to have a buffer. Well, okay, what is called the circular buffer of n slots. We have two processes. The idea is that we have two processes, process 1 and process 2, producer, for example, and process 2, consumer. We have a buffer, and you can, by the way, this is how a pipe, a named pipe works. So this is the algorithm used by the kernel to implement the first in, first out structure that is called pipe, that is a bounded buffer. But you may meet this problem, and you may have the idea of the need to implement it. It is surprisingly, even if the POSIX is process POSIX is low level, this is solved already by the kernel. If you are using shared memory, using threads or shared memory POSIX, you probably have to implement by yourself. So it's a reverse situation in which you are at a low level, you have some problem already solved. So in that case, the producer puts data in the buffer. And this is called circular in the sense that you want to use the whole buffer simultaneously. So the producer may write in the buffer while simultaneously the consumer reads from the buffer. Since they read and write different location, sometimes they could be allowed to enter the buffer, but normally to make it safer, the idea is that you consider the buffer as a shared resources. So just one, the consumer or the producer accesses the buffer just to deposit or to pick up the datum. And, but you have to take into account the length of the buffer and to stop the producer if the buffer is full. In the pipe case, the writer issues the write on pipe, but the pipe is full and the write is suspended. But you want also say that if the buffer is empty because the producer is losing time and doesn't produce new data, the consumer finds the buffer empty and is blocked, like reading from an empty pipe. Semaphore are the solution for that. So a possible scheme is that the producer wait for buffer not full, and there's you know that in the in pipe this may happen. Lock the buffer, deposit, unlock the buffer, and says the buffer is not empty, because if you have succeeded in writing the buffer has at least one possible new datum to read. The other side, the consumer waits for the buffer not empty, and you know that the role of the select in pipes reading, then locks the buffer, retrieve, unlock the buffer, not full. The lock buffer and unlock buffer in a sense are optional. If you're sure that in any case you do not read or write the same location inside the buffer, you may avoid to use locking or unlocking. Since the algorithm is much simpler, if you don't mind that, if you're not taking into account the fact that the two producer and consumer are not using the same slot inside the buffer, usually this is a solution. You put locking, unlocking. That means another additional semaphore. So you need two semaphores. A semaphore to protect the buffer, this semaphore, and another semaphore to block the consumer if the buffer is empty, and another semaphore for the producer if the buffer is full. So the solution, I hope that it is this one. So you are using a semaphore also as a counter. N is the number of slots in the buffer. Use two semaphores of this kind, and at the beginning, not full is N because the buffer is empty. So we have N possible writing action. Not empty start from 0. So if the consumer attempts to read, is blocked. The mutex often a semaphore in the jargon is called mutex. The jargon mutex, I forgot to say, to write in the first scratch pad. Is a jargon, and in some cases a technical name, is a binary semaphore for mutual exclusion. Binary semaphore for mutual exclusion. What is a binary semaphore? Is just a semaphore initialized at 1. If two processes are using a semaphore initialized at 1, the semaphore can have only the 1 and 0 value. Some semaphores are, for example, in threading, there are some semaphores that are called mutex, in which you cannot increment the counter more than 1, because you must use only for mutual exclusion between two threads or processes. So mutex is the typical term for a semaphore that in origin cannot have a value greater than 1, or if you want to use explicitly, in our case, all semaphores can have the counter with any value, but I don't want that the value is greater than 1. So the term is mutual exclusion between two processes. So you see, in the internal part of the producer-consumer codes, this area is protected by the mutex wait and signal. So this region of code is the critical region that is in any case executed by only the producer or the consumer, but not both, because the first one who issues the wait prevents the other to do the same, and vice versa. So if mutex wait, so mutex wait is issued by the producer, the consumer says mutex wait, okay, block the process. The process goes in the waiting states, waiting for the value of mutex to be given back the value 1 by the signal. So as soon as the producer leaves the region with the signal, the consumer starts, and vice versa in any case. But there are two other semaphores. They go in the opposite direction. In the beginning, for example, this not full is n. So the first run of the producer goes to n-1, n-2, and so on. But as soon as the not full weight is as soon si è fermata la rete. Guarda un po'. Can you?
We can see now.
So, okay,
we can see and hear.
Me?
Yes, we can see you and hear you now.
Okay, okay. I was some
for 10
seconds.
Problem.
I share the screen again. I just was telling that, starting from the beginning, the first time the producer puts a datum inside the buffer, raises the semaphore weighted by the consumer, and so the consumer is able to go on. So you see the couple, not full and not empty, are the couple that allow the consumer to go on as soon as they are data to read. And if the producer is slow, the consumer goes on, and anytime the consumer reads, decreases the value of not empty, so that so at a certain time it can stop because there are no data to read. The consumer is not able to signal because it does not pick up data. At the end, the producer will stop because it finds this semaphore at 0. So this is a solution, a typical solution of a producer-consumer. And let me. Okay, I shut down the telephone. Okay. There are several other slides, and in particular, the readers and writer problem. There is a generalization, in a sense, of the producer-consumer user circular buffer. It's much complicated, but have a look at this. I think it's interesting because they are another typical problems like the roller coaster problem. But we can stop we stop here. So I want you to know in particular the idea of using the semaphore for purely mutual exclusion. How they must be used, and the circular buffer, that is the implementation of the pipe by the kernel. So there are general ideas regarding semaphores, and I think they're easy to understand. And I want you to know and use this concept to read and learn the POSIX shared memory slides theoretically. Well, hope that everything was clear. I will upload these slides. They're not original and written by me, but I think it's really better than my slides in general. And I will just, next week, when we will comment all the topics for the exam, I will also give you some more detailed information about what we have to know and what is not necessary. But in general, all the materials in Aula Web are interesting for you. Okay, questions? I remind you that anytime you can ask me by writing on the on Skype, and on Saturday we will have question and answer as usual. Okay, so finish your second assignment and wait for the final assignment. Okay. Bye-bye. Thank you.
Professor. Bye.
Thank you, Professor.
Goodbye, Professor. Thank you.